Let's start with the basic definition of a limit. We say that L is the limit of a function f at x as x approaches a, if as x gets closer and closer to a without ever reaching a, f at x gets closer and closer to L. That's just a very basic definition of a limit, and here's how we would write that information. The limit as x approaches a of f at x equals L. And let me show you on a graph what I mean by this. So I have some function here, let's call it f at x. And I'm going to choose a to be at the x value of this discontinuity right here, because we might as well make it interesting. And I want to show you that the limit of this function, as x gets closer to a, would equal actually the y value of this discontinuity. And we'll call that limit L. So let me show you why the limit as x approaches a of this f at x function is that L value that I have labeled on the y-axis there. Well, if I were to look at what is the function doing as it approaches that x value of a from the left side of a. And by that I mean if I were to choose a few points whose x values get closer and closer and closer to a, and let me show you that those x values are getting closer to a just by connecting back down to the x-axis to show you those points' x values. As those x values of those points were getting closer to a from the left side of a, notice these points have x values to the left side of a, what's happening to the y values of these points? So let me connect these points to the y-axis so you can see their y values. And I'll label their y values f at x. Notice that the y values of this function are getting closer and closer and closer to this limit value I said it has. And there's actually a notation for this when we're getting points to approach the a value from the left side of a. I would say that the limit as x approaches a from the left side of a, and I indicate the left side by putting this little minus sign up there on the a, of f at x is equal to L, because the y values of the function, as x approaches a from the left, the y values are approaching L. What about if I choose points that are approaching the x value of a from the right side of a? So let's look at what's the function doing as I approach that discontinuity from the right. So if I choose, I'll just choose a couple points this time just so you can see what's happening here. As I choose x values that are getting closer to a from the right side of a, so as the x values of these points are getting closer to a, what's happening to their y values? The y values of these points are also getting closer to the limit L. So I'd say the limit as x approaches a from the right side of a, and there's a notation for the right side, it's that little plus, of f at x is also L. When the left and right limits are equal, we can conclude that that is the limit of the function. Let me show you in Desmos what this looks like as well. So notice I have a linear function here, and notice that when x is 3, y is 7, but let me show you that's also what the limit is as x approaches 3. As I let this point, that you can see I've got in purple showing the x and y values of this point, as the x values of this point get closer and closer to 3, notice the y values of this function are getting closer and closer and closer to 7, both from when I approach 3 from the left, and if I were to approach 3 from the right, notice the y values are getting closer and closer to 7 as well. Okay, now let's have a shot at trying to understand this formal or precise definition of a limit. It's going to be a little complicated and looks confusing at first, but really it's just stating something very simple. The formal definition of a limit says, we say that L is the limit of a function f at x as x approaches a, if for every epsilon greater than 0, there exists a delta greater than 0, that if the absolute value of x minus a is between 0 and delta, then the absolute value of f at x minus L is less than epsilon. And I'm going to show you what this means using a diagram, but it might be helpful for you to just interpret these things in words. This is the distance from x to a, and this is the distance from f at x to the limit L. Notice they're both in absolute value brackets because we just want the magnitude of the distance between x and a, or f at x and L. And what the definition of a limit says is that if we pick an x value that is within delta of a, then for sure we can guarantee that the distance between f at x and the limit is less than epsilon. And let me show you in a diagram what that means. It's often useful to think of it as we are given some epsilon value, which we can think of the margin of error between the function value and the limit. So let me show you in this diagram here that we can think of this distance here as our margin of error from the limit, and we call that epsilon. And often this is called the Epsilon-Delta definition of a limit. So if we want a function value that is within epsilon of the limit, there exists some delta value that, as long as we choose some x value within delta of a, the value of the function at that x value will be within epsilon of L. And actually, let me label these blue lines here. This is a plus delta, and this is a minus delta. And for the y values, this is the limit plus epsilon, this is the limit minus epsilon. Now, based on this definition, it tells me that as long as I choose an x value that is within delta of a, and let's actually pick one. I'll pick this right here. I'll pick an x value that is within delta of a. Any x value within delta of a is guaranteed to have a y value, a function value, within epsilon of the limit. And let me just show you the y value by connecting it to the y-axis. Notice the function value right here is within that margin of error epsilon that was created. And let me zoom in. This distance right here, the difference between f at x and L, and I'll do the absolute value of that just to get the magnitude of the distance. That distance, the length of that orange segment I drew there, is definitely less than the margin of error epsilon. And that's because the x value I chose is within delta of a. This right here, that's the distance between x and a. And notice that distance is less than delta. So as long as I pick an x value that is within delta of a, it guarantees that the value of the function is within epsilon of L. And it wouldn't matter what x value I chose within this range. Any x value in that range is going to give us a point on the function within this range, and all of those points have y values within epsilon of the limit. So that's the formal definition of a limit. That's the Epsilon-Delta definition. Okay, great. Well, what can we use this for? Let's have a look. Oh, and here's the same definition, just stated in a different way. Let me read it one more time for you. Maybe that'll help it sink in. This means that if you're given a margin of error epsilon of the function value, from the limit value L, there exists a distance from a, called delta, where any x value chosen between a plus or minus delta will result in a function value within L plus or minus epsilon. A simpler way of stating this is that we can make the values of the function f at x as close to L as we like by making x sufficiently close to a without letting it equal a. And actually, let me show you in Desmos how this works as well. So this same function that we were working with before, I'm going to move this point away a little bit. Let's say we were to create a margin of error from the limit that we wanted to make sure we were able to get within. So I've set those limits by adding and subtracting epsilon from the limit 7. There exists a range of x values, which we call delta, that as long as we pick an x value within delta of a, and in this case a is 3, as long as we pick an x value within delta of 3, then it would be guaranteed to have a y value of the function within epsilon of L. And let me actually shade these in so you can see them a bit better and you can see the overlap. And let me move this point. Notice that as long as I pick an x value within the orange region, the y value of the point is going to be within the green region. That's all this means. And we could make that margin of error as big or as small as we want, and there would always exist a range of x values that gets us within that range. the bigger we make the margin of error epsilon, the bigger delta is going to get. And the smaller we make epsilon, we can make it as small as we want. There's still going to be a delta away from the x value of 3, that as long as we pick an x value within delta of 3, we'll be able to get a y value within epsilon of L. All right, now let's see what we can use this for. So I'm going to calculate a limit from a graph here, and then I'm going to show you how we can use the precise definition of a limit to verify that answer we've got. So from this graph, let's find the limit as x approaches 3. Well, I know to find the limit as x approaches 3, I have to check the left and right hand limits of it. So let's look at what is the function doing as I approach the x value of 3, and let me just label the x value of 3 here. What is the function doing as I approach that x value of 3? Well, notice there's actually a discontinuity when x is 3. The function's actually up here, but with a limit, we don't care the actual value at 3. We care what is the function doing as it gets close to 3, but not equal to 3. So as I approach an x value of 3 from the left, let me actually do that in a different color. What is the y value of this function approaching? So let me pick a couple points here. And as those points move closer to an x value of 3, so as x approaches 3 from the left side of 3, what's happening to the y values of these points? What are they getting close to? What are they getting close to? Well, I can tell it looks like it's going to get closer and closer and closer to the y value of that discontinuity, 5. So I could conclude that as these points moved closer and closer to 3 from the left of 3, the y values of the points are going to get closer and closer to 5. So I will say the limit as x approaches 3 from the left side of 3 of f of x equals 5. How about if I approach 3 from the right side of 3? So as the function approaches 3 from the right side of 3, let me just pick a couple points on the function that are getting closer to 3 from the right side of 3. So as the x values of those points get closer to 3, what's happening to the y values? Notice the y values are getting closer and closer to 5 as well. So I can say the limit as x approaches 3 from the right side of 3 of the function equals 5. Since the right and left limits are equal, we can conclude that the limit as x approaches 3 of f of x equals 5. And this would be a good time for us to actually state an important rule for limits. If the limit as x approaches a of f of x exists, the following 3 criteria must be met. The limit from the left exists, the limit from the right exists, and the left and right limits are equal to each other. Now let's go ahead and use the Epsilon-Delta definition of a limit to answer part B. It says, how close to 3 does x have to be so that f of x differs from 5 by less than 0.1? So basically, I've zoomed in really closely on this part of the graph right here. Because at that point in the graph, we know that at this continuity here, the x value is 3. So at that point on the graph, the question gives us a margin of error. It says epsilon is only 0.1. Well, I know the y value of this discontinuity was 5. That was given to us in the graph. And that was our limit. The question says we want the margin of error to only be 0.1. We want epsilon to be 0.1. And then if epsilon is 0.1, what is delta so that any x value picked within delta of 3 will give us a y value within 0.1 of 5. Let me show that on this diagram. I'm going to exaggerate 0.1 a little bit, just so I have a little bit more room to draw on here. Let's say that this is 5.1. And if this is 0.1 less, this is 4.9. So our margin of error, this right here, is our epsilon, and that's only 0.1. So if epsilon is only 0.1, the question is saying, what is delta? And let me zoom in and label delta here. So that any x value chosen within delta of 3, so any x value chosen in this range, will result in a y value on the function that is within epsilon, in this case 0.1, of 5. So let's calculate delta. What is this delta value going to have to be? So let me write out the definition of a limit again. The definition of a limit tells me that if the difference between x and a is less than delta, then the difference between f at x and the limit is going to be less than epsilon. And in this question, we know a lot of these values. The a value is 3. So we could say if the absolute value of x minus 3 is less than delta, then f at x, the function, well, if we look back up to the previous question, the function value was 2x minus 1 as long as x isn't 3. So I can say 2x minus 1 minus the limit, which we calculated in the previous question as 5, is less than epsilon, which the question tells us is 0.1. Now, my goal now is to figure out, well, what value of delta makes this true? What value of delta, where as long as x is within delta of 3, f at x is going to be within epsilon of 5. To figure that out, the strategy is going to be trying to make this look like this. So let's algebraically try that. Let's just start simplifying this part of our statement here. So 2x minus 1 minus 5 is 2x minus 6. And I could common factor a 2 from 2x minus 6 to get 2 times x minus 3. And notice it's starting to look the same. I just have this factor of 2 inside the absolute value brackets. The absolute value of 2 is 2, so I can take that out. And then I can divide that 2 to the other side. 0.1 divided by 2, well, half of 0.1 is 0.05. So I can see from my statement here that if x minus 3 is less than delta, then x minus 3 is going to be less than 0.05. So I can make my concluding statement that says that if the difference between x and 3 is less than 0.05, then the difference between the function and the limit, which was 5, is going to be less than 0.1. So as long as I pick an x value within 0.05 of 3, I'll get a function value within 0.1 of 5. And let me just show you on my diagram here. We just figured out that the delta value is 0.05, which makes these points 3.05 and 2.95. So as long as I pick an x value between 2.95 and 3.05, I can pick an x value right here, the value of the function at that x value is going to be within epsilon of 5. So it's going to be between 4.9 and 5.1. And notice it's right here. The difference between f at x and the limit is clearly less than epsilon 0.1. Let's do one more type of example with the precise definition of a limit, the Epsilon-Delta definition. It says use the precise definition of a limit to prove that the limit of 4x minus 5 as x approaches 3 is 7. Well, the precise definition of a limit, let me write that out again. It says that if the difference between x minus a is less than delta, then the difference between f at x and L is less than epsilon. And let's plug in what we know from this question. In this question, our a value is 3. And we know the value of the function. The function value is 4x minus 5. And it says to prove that the limit is 7. So I'll sub in 7 for the limit. Now I don't have a value for epsilon or delta, but I should be able to see the relationship between the two to prove that this in fact is the limit. If for any value of epsilon there exists a value of delta, then I've proven that 7 is the limit. And the way we prove that is, once again, is by trying to make 4x minus 5 minus 7 look like x minus 3. So let's just work with my right statement here. collect my like terms. -5 minus 7 is -12. Common factor of 4 from both of those terms. And then the absolute value of 4 is 4, so I can take that out. And then I'll divide the 4 to the other side. So the difference between x and 3 is going to be less than delta if the difference between x and 3 is less than epsilon over 4. So my final statement will say, if x is within epsilon over 4 of 3, then f at x will be within epsilon of L. So you could set the margin of error to any number you want, and then delta will just be 1/4 of that, and it'll work. Jensen Math.